My name is Anastasia Babkina, and as Marina Nikolaevna said, I have a good English level. That's why I will speak in English. Sorry for that. I'm specialized in glass mostly, and mostly in glass with transition metal ions. So for me, as the person who is working with transition metal ions, there are too many rare earth ions on this conference. Really, rare transition metal ions. But now I will talk about nanocrystals inside of the glasses. So what are perovskites? Perovskite macrocrystals or monocrystals of this composition are known like for a very long time, for about 70 years, because the first macrocrystals were synthesized, were grown at about around 1950s. So first optical properties and first modulation of their properties and crystal structure and band structure were made at 1950s. Long story short, in 2014, a paper was published concerning these crystals, but made in a solution. And surprisingly, they do have very luminescent properties inside of the solution. For example, they have quantum yield, absolute quantum yield of about 100%. And at that moment, like scientific society said like, wow, 100% is very cool. So let's do it every day. Let's synthesize these perovskite nanocrystals in solution every day. So since 2014, there is a lot of papers concerning these nanocrystals inside of the solution. And yes, they do have very high quantum yield. If we are talking about bromide crystals, they have luminescence in green region. If we are talking about iodine, they have in red, and chloride crystals, they have luminescence in the blue region. So we have perfectly ideal RGB with a very high quantum yield. But the problem with these nanocrystals inside of the solution is that they are not stable. I think people that are working with the halogen crystals, monocrystals, they know that they like to interact with the oxygen in the air. That's why they usually lose their properties in some days or maybe some weeks. So here is the same. Perovskite nanocrystals inside of the solution lose their properties and their intense luminescence in maximum like several weeks. And the problem arises to, of course, stabilize them. But is the main question. First idea was to stabilize them by polymer matrices. So I'm not working with polymers, so I liked the second idea, is stabilize these nanocrystals by the glass matrix. And starting from 2016, such papers arise. The first paper just showed us the possibility that these glasses with such nanocrystals can be made. And they, of course, they were made, and you see them here, it's the first one, inside of the phosphate glass matrix. But quantum yield was not mentioned by the authors. And it's very suspicious, you know, that very highly luminescent nanocrystals inside of the glass, are they luminescent indeed or not? So after that, other papers arrived, this one and this one. And as you can see from the slide, the maximum quantum yield was achieved as 44%. Yet it's twice less than 100%, you see. But these nanocrystals are in glass, and they're fully 100% stable, as the glass can be stable itself. But as you can see also on the slide, in this picture, you see that the glasses are very strange, you know? They are not very really transparent, and sometimes they don't look like glass, and offers even grinding them to make a powder. It's really very strange for all glass makers, because when you synthesize a glass, the first thing that you should make is to make a photo of it to prove that it is really glass, it is really transparent, and it is a glass that you can hold in your arms, and it will not melt in them, you know. So, but still, some papers have shown us that yes, it is possible, and you can obtain perovskite nanocrystals of different compositions inside of the glass matrix. The second peculiarity about all these papers is that they were done mostly by Chinese scientists. So we decided to take part in this race and also to synthesize glasses with the perovskite nanocrystals. So as you see, our first attempts, they are good, but not enough good, because the glasses are not very uniform, as you see. But still, we take borogermanate glass matrix, use the bulk crystallization method, and obtained at different temperatures and of heat treatment, and using different duration of heat treatment to obtain nanocrystals inside of the glass matrix. And you can see we have these nanocrystals and these nanocrystals, so bromide and iodide nanocrystals of cesium lead perovskite. The most lovely thing about nanocrystals inside of the glass matrix is there we can vary its size by varying the regime of heat treatment. And the second lovely thing is that all these crystals are of the nanoscale, not of the macro scale, but the nanoscale. So we are working inside of the region of the size effects. What does it mean? It means that while raising the temperature or the duration of the heat treatment, the mean size of the crystal increases with it, and the luminescence wavelength maximum, wavelength of the luminescence maximum, and exciton absorption maximum, they are shifting towards long wavelengths. It means that if we are working, for example, with the bromide crystals, we can vary the luminescence from like 450 nanometers up to almost 550 nanometers, so by 100 nanometers in the visible spectrum. If we are talking about iodide nanocrystals, as here, you can see that we vary it almost by 100 nanometers in the red region of the spectrum. And that is very good for us. The glasses that we have obtained with nanocrystals have a quantum yield really good enough. If we are talking about iodide nanocrystals, the maximum quantum yield that we have obtained is 33%. What about literature and other scientific groups? Other scientific groups have not opportunity to obtain these nanocrystals inside of the glass matrix with such quantum yield. The maximum quantum yield of other groups in the world was 4%. So we obtained 33, and I think this is a success. Sorry. What about bromide nanocrystals? Here, a very peculiar thing happened, because usually bromide, cesium lead bromide perovskite nanocrystals have the most intense luminescence comparing with other crystals with other halogens. But in our case, we obtained glass with these nanocrystals with a maximum quantum yield of 15%. So I think that in this case, we will work further to improve it. Sorry. But you know, pure halogen perovskite nanocrystals are not very, because you know, everybody are making them. So we decided to make mixed halogen perovskite nanocrystals. Firstly, we took bromide and iodine ions, because you know we have synthesized bromide perovskites and iodide perovskites. Why not mix them? We made a glass roll at different temperatures. We also heat treated them. As you can see, at daylight and under UV lamp, they have different color of luminescence. And by combining bromide and iodine ions inside of the composition of nanocrystals, it perhaps can help us to tune the luminescence from the beginning of the green region of the spectrum up to the end of the red region of the spectrum. So we will cover like 2 out of 3 parts of visible region. So what about quantum yield? Quantum yield at the moment here, standing me right here, the biggest one is 28%. I think that we can make it better, really. And as you see from the pictures, the samples of the glass, they are more uniform than the first one. So the previous samples were the first. The samples that we have obtained, these are the last in neighbor. So these are luminescent spectra of these mixed perovskite nanocrystals. As you can see, they also shift from almost 500 nanometers up to 700 nanometers, so 200 nanometers we tune. What about absorption spectra? It is really very interesting because when we are talking about mixed nanocrystals, we really don't know if they are mixed inside of the glass matrix. What does it mean? It means that, for example, these crystals cannot be mixed, but they are just like sitting inside of the glass matrix simultaneously, but separately. In this case, they can produce 2 bands of luminescence, but you have seen that we have only 1, but in some cases we have like 2, really. The problem with this luminescent spectrum is that we have not got very selective excitation. Our excitation is really very, very wide, and maybe that is our problem, that because of it, we don't see 2 bands of luminescence. What about absorption spectrum? Looking at the absorption spectra, we do have several bands. The first band in the long wavelength region, of course, corresponds to the iodide perovskite nanocrystals. Absorption band that is situated in the short wavelength region, about 500 nanometers, corresponded to the bromide crystals, and we see it separately. You see, separately. So we try to tune the excitation wavelength of our to excite our luminescence, but we still have one band, but very, very wide luminescence band. Okay, so some chemical results. We, of course, studied the chemical composition of our glass, because the chemical composition that I showed you before is the chemical composition of the glass batch. When we synthesize the glass, we have a lot of elements volatile out of the glass. So the final chemical composition of the glass is not the same as the chemical composition of the batch. And here we see that elements that form our nanocrystals, they volatile a lot. And if we look at the iodine, it volatiles by 10 times. And this is really very pity because we lose a lot. But we tried our best, I think, in future, and maybe we will make this volatility smaller. What about X3D? Of course, when we're talking about nanocrystals or other crystals inside of the glass matrix or whatever, we of course need X3D. The problem with the nanocrystals is that when we are working with nanocrystals, with a small number of nanocrystals inside of the glass matrix, we see luminescence and we see the absorption spectrum, because you know the intensity of the exciton absorption is really very high. That's why we need low concentration of crystals to be inside of the glass to measure absorption spectrum. But when we have low concentration on the crystals, it's the problem to measure X3D, because they're very small. Its quantity is very small, and they have dispersion in size. Because it is a usual thing when you obtain nanocrystals inside of the glass polymer also. So if we tried our best and make very, very concentrated glass with a very high concentration of nanocrystals, then in that case we can obtain such extraordinary results. And if we look at the compositions only with bromine ions, we see that we have reflexes corresponding to cubic perovskite phase and to parasitic phase, cesium-4, lead, bromide 6, but in less quantity. If we look at the composition with mixed bromine iodine ions, we still see only the same phases. So what is it? Where is the iodine? The problem is that when we are dealing with the perovskite crystals with the same crystal modification, the reflexes of them here will be very close. And because we're dealing with very small crystals with the sizes less than 10 nanometers, the reflexes are really very wide. You see, they are wide indeed, comparing with monocrystals. And that's why maybe these reflexes contain both bromide perovskite and iodide perovskite at the same time, but we cannot distinguish them separately. Maybe, or maybe not. So we're still in progress. And of course, when we are talking about unstable systems, namely perovskite nanocrystals, we are, as I said before, in solutions they are not stable. In the form of monocrystals, they aren't stable. So stable, but not very good, really. When we put them inside of the glass, we can make measurements of their chemical durability according to the international ISO, International Standard Organization, that standardize all optical materials that are used in optical schemes. So it's the thing for I don't know, for all optical materials that are used in massive production. And I made side tests of chemical durability, and still I can say that these glasses are stable enough for the massive production. So it means that we can take very unstable nanocrystals that destroys in several weeks, put it inside of the glass matrix and make them very unstable. This material will have a life longer than we all will have. So after our death, they still will exist and will be luminescent. Most part of these results are published in this paper. Here, there's a collaboration between our group, St. Petersburg Polytechnic University, and St. Petersburg State University. I'm working in Research Center for Optical Material Science. The head of our center is Professor Nikolai Nikanorov. This is me and my dream team, my girls, as I call them. We're situated in St. Petersburg, near the main building of the St. Petersburg State University. My colleagues, they are also working with glasses, nanothermometers, and so on and so forth, many kinds of optical materials. Also, as I said, I'm working, and my team, we are working with glass ceramics with manganese ions. So 4 plus manganese, manganese 4 plus, manganese 2 plus, and with chromium ions. So thank you again for your attention, and we are open for collaborations.
Thank you. Okay. The questions?
Yes, may I ask a question?
Yes, please.
Yes, thank you for a very interesting presentation. And the question is not really directly connected with your talk, but is that possible to grow bulk single crystals of these perovskites?
Inside of the glass, we can't do that. So because the growing of crystals inside of the glass is the diffusive process, we are working with the oversaturated solid solution inside of the glass. And and we induce diffusion by making heat treatment. That's why we can't grow a single crystal. There will also be a lot of crystals inside of it, and they will be disorientated according to each other.
Oh, I see. But do such crystals exist?
Yes.
By other method, maybe.
The perovskite cesium lead halogen crystals do exist, but that are not mixed. So we only have one halogen. They do exist. There are some papers and there are photos of them that are proving that it is crystals, but not very good quality, but they do exist. Yes, but not mixed.
Yes, okay, thank you.
Thank you, thank you. We have two online comments and questions. First questions from Vladimir Pankratov. His comment and question, low light yield from your samples most likely is due to interface defects by analogy with embedded C nanocrystals. Do you to passivate such defect by thermal treatment in specific atmospheres?
When I was showing you the defects on the surface of the samples, it was concerning only the chemical durability tests. Really, we can do samples without surface defects, and these surface defects do not affect the properties of nanocrystals because nanocrystals are inside the glass matrix and are surrounded and protected by it. So the surface of the sample and nanocrystals do not interact between each other.
Thank you. And the second question is from Andreas Meyering. Wonderful presentation. For the bromine and also iodine nanocrystals, you see a large spectral shift. This means that the particles are very small, smaller than the colloidal and CS. Do you know this size?
Thank you for your question. It's a very good question. And yeah, the size is our problem because when we have such big shifts, it means that we are working in the terms of a quantum size effect, and it means that our nanocrystals are less than exciton Bohr radius. For bromide crystals, exciton Bohr radius is 7 nanometers. For iodide, it's 12 nanometers. So it means that for both cases, our nanocrystals are less than this number. And XRD can't properly help us to obtain this size. TEM also, by this moment, couldn't help us. The only thing that we can do is to take spectroscopic results, namely the absorption spectra at low temperatures, and use the mathematical theory described and designed by Efros in 1982 concerning the size of semiconductor quantum ball. Yes, we use this model, and we calculated that indeed our nanocrystals can be synthesized in sizes starting from 2 nanometers up to 7 nanometers.
From 2 up to 7.
From 2 up to 7.
Okay. Thank you. And second question is from Andreas. Have you done luminescence lifetime measurements to better understand the quantum yield?
Mm-hmm. Yep. Yes, thank you for the second question. Yes, we have made luminescence lifetime experiments. And the results was very tricky, you know, and that's why I haven't shown it here, because almost for every for every glass sample with different crystals, the average lifetime was about 10 nanoseconds. And this is okay for these crystals, but it was not right by like thermal heat treatment, duration or temperature, and it was very peculiar. So we are working on it now.
Thank you. И последний вопрос. Онлайн, он по-русски написан, я не буду переводить. Образуются ли кислородные центры в кристаллах перовскитов в процессе синтеза стекол? Попадает ли кислород туда?
Скажем так, ответ на этот вопрос немножко выходит за рамки моей экспертности.
Соображения, может быть, какие?
Да, соображения. Скажем так, такое может быть. Такое вполне может быть, потому что всегда, когда мы работаем со стеклом, мы всегда получаем внутри него так называемый твердый раствор. И твердый раствор — это может быть, соответственно, включающий в себя компоненты самого нанокристалла, то есть, собственно, отсутствие кислорода, и компоненты стекла. Собственно, компоненты стекла содержат кислород в огромных количествах, поэтому такое может быть. И, к сожалению, скорее всего, если даже мы захотим от этого избавиться, мы это сделать не сможем.
Как-то вы можете проверить, что есть кислород?
Ну, только если когда-то кто-то выращивал монокристалл и там и обнаружил, и подтвердил, что это сильно кислородная вакансия, мы можем сравнить результаты с их результатами.
Так, ну и последний вопрос.
Thank you for your presentation. My question, what are the process parameters do you tune to increase quantum yields?
What process parameters can we use to increase?
Yes.
There are a lot of process parameters because it is technology. It's glass technology. It means that we can vary 10 components of the glass composition. We can vary the temperature and the duration of glass synthesis, the speed of the rotation while homogenizing the glass melt. And we can obtain and vary different the parameters of heat treatment. So we have about 20 variables in this technology, and by all of these, we can induce or reduce quantum yield.
Okay, thank you.